Hello there and welcome back to the Science Sleepy Minds. You're drifting now, gently, weightlessly, through a void that doesn't quite feel empty. Ahead, there's a darkness so complete it bends the stars around it, a celestial smear in the fabric of the universe. But even as your eyes adjust to the black, something utterly strange erupts from its poles. Streams of blazing light, so bright they outshine entire galaxies, piercing the infinite dark like lighthouses powered by doom. You're staring at a black hole, and somehow it's shining. Welcome to one of the most confusing, exhilarating paradoxes in astrophysics. How the universe's most lightless objects can become some of its brightest. You probably won't survive this. You're getting dragged towards something where time stops and gravity eats math for breakfast. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And drop a comment with your location and what time it is where you are, because some of you are watching from the future, I swear. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You begin your descent near a supermassive black hole, say, the kind lounging at the centre of a galaxy, like the monster Sagittarius A star in our own Milky Way. As you approach, your thoughts get heavy, and not just from the gravity. Everything here is extreme. A star could orbit this thing at tens of millions of kilometers per hour and still not break free. Space is folded in on itself like a cosmic pretzel. Light, usually your friend, now curves and flexes in bizarre ways around this massive object. But what hits you next isn't the pull, it's the flash. Like twin laser beams slicing the dark, jets of high-energy particles shoot out of the black hole's poles at near-light speed. They're so intense they span hundreds of thousands of light years. And no, they're not coming from inside the black hole. That would break the rules. They're formed just outside the event horizon, in that narrow, chaotic region where matter spirals inward and physics begins to unravel. Here's the twist. Black holes themselves don't emit light. By definition, they're the ultimate one-way door. Anything that crosses their boundary, the event horizon, gets added to the black hole's mass and disappears from the observable universe. So how do these incredible light shows occur? How can something that traps even photons power a display that outshines entire galaxies? The answer lies in the violent borderlands of the event horizon. Matter doesn't just fall straight in. It spirals, slams, compresses and heats up in an accretion disk, an orbiting platter of cosmic chaos. The material in this disk, plasma, dust, gas, even shredded stars, gets crushed and superheated as it approaches the black hole. Temperatures climb into the millions of degrees. The disk glows fiercely, blasting out X-rays and gamma rays before vanishing into the void. Still with me? Good. Because here's where it gets weirder. As the black hole spins, and they often do, some at nearly the speed of light, it drags space-time itself around with it. This frame-dragging effect twists magnetic fields into tight, unstable spirals. Imagine spaghetti noodles of magnetism getting tangled by a god-tier blender. Under these wild conditions, some of the infalling matter doesn't fall at all. Instead, it gets flung out along the black hole's rotational poles, channeled by those wound-up magnetic fields. What erupts is a jet, a high-speed collimated beam of plasma and radiation that escapes the system entirely. This is where darkness makes light. You're not the first to be mesmerized by this. In fact, humanity's first encounters with these jets came through radio astronomy in the early 20th century. Astronomers noticed huge lobes of radio emissions coming from deep space before anyone had even proven black holes existed. The phrase quasar, short for quasi-stellar radio source, entered the scene in the 1960s, and no one could figure out what the heck these things were. Stars? Galaxies? Aliens? Is never aliens, probably. Eventually it clicked. these bright beacons were coming from the cores of distant galaxies, powered by something unseen, something compact and ravenous. Today, we know they're almost always supermassive black holes, some billions of times more massive than the Sun. Historians still argue whether the concept of black holes even made sense before the 1970s, when scientists like Stephen Hawking and Roger Penrose formalised their properties. Before that, they were more like mathematical curiosities, but nature had clearly been making and using them for eons, and here's a delightful fringe nugget. There's a theory, only half-jokingly proposed, that if aliens were trying to communicate across galaxies, they'd hijack a black hole jet. Why? Because it's a natural spotlight visible across millions of light years. You just modulate the beam, Morse code style. Again, probably not aliens. But if it were, chef's kiss for drama. Back in your imaginary spaceship, you drift sideways from the jets to admire the scale. The jets coming from some black holes stretch for millions of light years. That's not a typo. The galaxy M87, whose black hole was famously imaged in 2019, has a jet extending 5,000 light years, and that's just what we can see. If our sun were parked in the path of that beam, instant disintegration. No SPF could help you now. But here's a fun bit of cosmic irony. While the black hole's gravitational pull is unbeatable, the jets are one of the only things in the universe that can fight gravity. They don't just escape it, they redefine the local structure of space. Wherever they go, they punch holes through galactic gas clouds, heating some areas and cooling others. In the long term, these jets help sculpt the galaxy itself. You pause to take in the view, one direction, complete darkness, the maw of inevitability. The other, blinding streams of light, heat, and matter. Both born of the same engine, a thing so gravitationally greedy it can trap light, and yet paradoxically it becomes a cosmic spotlight. And that's just the beginning. You drift a little closer now, not dangerously close, not yet, but enough to see spacetime doing some truly unsettling things around the black hole. It doesn't behave like a simple pull of gravity, like an apple falling from a tree. No, gravity here warps and twists, lines that should be straight curve like brushstrokes on a Salvador Dali canvas. Your internal compass? Useless. Time stretches, light bends, and every sense of direction folds in on itself. Welcome to relativistic hell. Einstein's general theory of relativity predicted this very thing back in 1915, that massive objects warp space-time around them, and black holes, especially the supermassive ones, take this to the extreme. You're not just dealing with a dent in the fabric of space here, you're spiralling toward a pit that drags the fabric with it. Think trampoline, but with a bowling ball the size of a city pulling the entire gym floor downward. This isn't science fiction, we've measured it. When astronomers track stars orbiting Sagittarius A star, the black hole at the centre of our Milky Way, they notice something bizarre: the orbit's precess. That means instead of tracing perfect ovals like planets around the Sun, the stars do slow, weird spirals, proof that space-time itself is twisted. One star, known as S2, orbits this monster every 16 years, reaching speeds of 7,650 kilometers per second. That's about 2.5% the speed of light. The poor thing is basically drifting through a giant cosmic whirlpool. Historians still argue whether Einstein ever truly believed black holes could exist in reality. His equations allowed for them, sure, but he was reportedly uncomfortable with the idea of something swallowing space and time entirely. Some physicists even tried to prove they were mathematical nonsense, and then the universe promptly dunked on them by building black holes everywhere. Now picture this, you're floating near the accretion disk again. This disk isn't flat like a dinner plate. It undulates, warps, and sometimes tilts, depending on the black hole's spin and the material falling in. But what's really disturbing is the sense that time is acting wrong. If someone were watching you from a distance, they'd see you slow down. Not mentally, not physically, but your clock. As you get closer to the event horizon, your seconds stretch into minutes, then hours. To the distant observer, you'd appear frozen, eternally suspended on the edge of doom. To you, though, time feels normal. You check your watch. Tick, tick, tick. No big deal. Meanwhile, billions of years could pass outside. Here's where things get philosophical. What even is time when it's so easily mangled? If your past, present and future are all warped by proximity to mass, is time an illusion? Do you experience moments in order, or just think you do? Welcome to black hole physics, where your concept of yesterday might get swallowed before your breakfast. There's also something deeply creepy about the idea of frame dragging. That's when the black hole's rotation pulls space-time around with it, like water swirling down a drain. It's not just that space is bent, it's being twisted. Imagine trying to walk on a moving sidewalk that keeps changing direction. Now replace the sidewalk with the fabric of existence, and you'll get a sense of how disorienting this place really is. And oh yes, the rotation matters. Black holes don't just sit there, they spin. In fact, some spin at nearly the speed of light. This changes everything. The faster a black hole spins, the closer matter can orbit without falling in. There's even a region called the ergosphere, outside the event horizon, where things get even weirder. In this zone, nothing can remain still, not even light. You're forced to rotate with the black hole whether you want to or not. It's like being caught in a planetary conga line with no off-ramp. And yet, here's where the beauty creeps in. Because of these bizarre distortions, you get some of the most stunning visuals in the universe. Light from the far side of the black hole bends around it, making the back look like the front. The accretion disk appears to loop over and under the black hole like a luminous crown. What you're seeing isn't just a fiery disk, it's a light show composed of pure relativistic weirdness. Here's a fun fringe theory. Some physicists once toyed with the idea that if you could orbit a spinning black hole at just the right distance, you could perform closed time-like loops. Basically, time travel. Go around once and you come back before you left. Unfortunately, the math breaks down faster than your sanity would. Plus, even if it did work, you'd have bigger problems like, being torn apart by tidal forces. Minor detail. Oh, speaking of those, ever heard of spaghettification? It's not a dish. It's your fate if you fall into a non-spinning black hole feet first. The difference in gravitational pull between your head and your toes stretches you like pasta. You become a human noodle. With spinning black holes, it's slightly less dire. Depending on the size, you might actually pass the event horizon without immediate doom. But eventually, still noodles, you're hovering now just outside that point of no return. You can feel the space around you thinning, flexing, moving like warm taffy. Particles streak past you, some inward, vanishing forever. Others, caught in that strange balancing act between gravity and motion, whirl around the black hole at insane speeds. Light gets trapped in orbits, circling the black hole like confused bees. And yet, in all this chaos, structure somehow emerges. The magnetic fields, twisted by the spin and shaped by inflowing matter, begin to guide energy upward and outward. These fields aren't gentle, they're violent, tangled things. But over time, they align. They form a funnel, and that's where the jet begins. One last twist of space-time. In 2022, scientists confirmed that the black hole in M87, the one whose image stunned the world, also showed signs of frame dragging in action. The light in its disk rotated visibly over time. We're not just talking about abstract math anymore, we're watching space-time bend in real life. And as you float there, quietly awed and mildly panicked, you realize something almost poetic. The darker the gravity, the stranger the light. You edge closer still, now drawn helplessly toward the shimmering boundary that defines a black hole, the event horizon. Sounds cool and mysterious, right? Don't let the name fool you. It's not a place you visit. It's a one-way street, a cosmic no-return policy. And the moment you cross it, you're no longer part of the observable universe. You're just gone. No rescue mission, no signal, no sequel. The event horizon marks the limit where escape velocity equals the speed of light. That means for anything to get out once it's past that edge, be it light, a message, or a slightly panicked astronaut, it would need to travel faster than light. And that, according to Einstein and all the physics textbooks collecting dust on your shelf, is impossible, at least for now. But here's the kicker, you don't feel a thing. There's no alarm, no sudden jolt as you pass through. From your point of view, it's just another moment. Tick, tick, tick. What makes it so unsettling is that everything outside sees something different. To them, you appear frozen in time, hovering forever at the edge, your image dimming and stretching as light from you struggles to escape and fails. It's like your final selfie gets blurred and redshifted into oblivion. Historians still argue whether the term black hole was really coined by physicist John Wheeler in 1967, or if it quietly existed in military slang before that. But by the late 1960s, the concept finally shed its reputation as just a quirky footnote in relativity math. Scientists began taking the idea seriously. They had to, because nature was being a bit too obvious about it. Back to the present, or whatever time is doing right now. You're watching as the accretion disk outside the event horizon burns hotter and brighter than the core of a star. It's still not inside the black hole, mind you. Everything you're seeing, every photon blazing your eyeballs, is from material circling just above the point of no return. That's key. Black holes don't shine. What shines is the matter falling in. And oh boy, does it put on a show before it disappears. Temperatures in this region can hit hundreds of millions of degrees. Plasma, ionized gas stripped of its electrons, gets whipped around at relativistic speeds, smashing into itself, emitting bursts of X-rays and gamma rays. If you had X-ray vision like a space telescope, you'd see black holes lighting up the sky like cosmic bug zappers. But again, not the hole itself. The hole remains dark. Always. Unless it doesn't. Here comes your quirky tidbit of the night. In 1974, Stephen Hawking proposed something wild. What if black holes aren't entirely black? What if, thanks to quantum effects near the event horizon, they emit a tiny trickle of radiation? This Hawking radiation, as it's now called, suggests black holes might slowly evaporate over billions of years, giving off faint whispers of heat. Yes, it's theoretical. No, we haven't detected it yet. But it raised a terrifying philosophical paradox. If black holes evaporate, what happens to all the information they swallowed? Is it gone forever? Does that break physics? This debate has raged for decades. Some physicists say the info is lost. Others argue it's preserved in some scrambled form. And recently the pendulum has swung toward information must survive. But no one's agreed on how. Even Hawking waffled on his position late in life, which just tells you how deeply weird this problem is. The stakes? Oh, just the foundational laws of the universe. No pressure. But back to you, bravely floating in the kill zone of this monster. The gravitational pull is so strong here that even light bends around the black hole, not in a lazy arc, but in wild, looping orbits. At a precise distance, called the photon sphere, light can actually circle the black hole, literally orbit it. Imagine a beam of light trapped in a racetrack made of space-time curvature. Stay too long though, and it'll spiral inward, devoured like everything else. You wonder what this means for those brilliant jets you saw earlier. If nothing escapes the black hole, how do these high-speed beams blast away from its poles like angry lighthouses? Patience. That's coming soon. But first, let's take a moment to appreciate what a black hole actually is under all this terrifying drama. It's a singularity, an infinitely dense point where the math of general relativity breaks down. Not just very dense, not just super heavy, infinitely. Imagine compressing Mount Everest into a sugar cube, then compressing Earth into a marble, then the sun into a city block, then keep going. The singularity isn't a place you can point to. It's the point where our understanding of physics bursts into tears and needs to lie down. and you're getting closer. Around you, time dilation is getting intense. The faster you move and the stronger the gravity, the slower time passes for you compared to the rest of the universe. From your view, the cosmos is speeding up. Galaxies race past in fast forward, stars are born and die in seconds, civilizations rise and fall like blips. It's kind of like binge-watching the entire history of the universe in 4K, without the snack breaks. There's something eerie about being this close to ultimate silence. No sound can travel here. Space is a vacuum. And yet, your mind fills the silence with imagined rumblings, with the ghostly echoes of plasma jets and swirling gas. You're on the edge of a cosmic chasm, and it feels like standing at the rim of a volcano, waiting for the lava that never arrives, because it already swallowed you, and you just haven't noticed. Oh, and let's not forget the innermost stable circular orbit, ISCO. That's the closest a particle or photon can orbit the black hole without spiraling inward. For a non-rotating black hole, it's 3 times the Schwarzschild radius, the radius of the event horizon. But for a spinning black hole, that limit shifts. In fact, for the fastest spinners, the ISCO can get dangerously close to the edge, meaning more energy can be extracted from the accretion disk. Which brings us to a strange implication. The faster a black hole spins, the more efficient it is at turning in falling matter into outgoing light and energy. Some theorists estimate that the process can be up to 40% efficient. For comparison, nuclear fusion, the power of stars, is only about 0.7% efficient. Let that sink in. Black holes are some of the most efficient engines in the universe. You're still floating near the horizon. You haven't fallen in yet. And all around you, particles and photons are dancing their last dance, spiraling inward in a fiery blur. They're not just dying, they're contributing, feeding the beast, yes, but also lighting the universe in ways that inspire entire fields of study, fuel giant radio telescopes, and maybe, just maybe, make someone on Earth look up and say, "What was that?" So take it in, the light around the darkness, the violence at the threshold, the calm within the scream. Because from here, the jets begin. You finally see it clearly now, the source of that terrible brilliance. It's not the black hole itself, of course. That still looms as a perfect absence, a hole not just in space, but in logic, in expectation, in the very idea of being seen. No, what glows with a vengeance is the disk around it, the accretion disk. It's not what you'd call stable. This is no dainty ring of stardust gently spinning its way to cosmic oblivion. The accretion disk is a screaming maelstrom of plasma, a roiling carousel of shredded gas, solar debris, and the occasional unlucky star, flattened, compressed, heated to absurdity. If you've ever seen a pancake get too close to a stovetop flame, imagine that. But 100 billion degrees hotter and travelling at nearly the speed of light. You've heard of nuclear furnaces. This is something else entirely. The accretion disk glows with high-energy radiation, X-rays, ultraviolet, some visible light if you're lucky, and it's so bright it can actually outshine the entire galaxy that hosts it. That's not hyperbole. These disks can emit thousands of times more energy than the combined light of hundreds of billions of stars, which is hilarious if you think about it. The ultimate destroyer, the gravitational endgame, wrapped in the most flamboyant tutu of light imaginable. Now here's the thing about these disks. They're thin, ridiculously so. For something that might span several light years across, they're often only a few light minutes thick. It's like a dinner plate stretched to galactic proportions, spinning fast enough to bake atoms. And because of this structure, most of the jet launching action happens right above and below the central region, where conditions get spicy. Historians still argue whether the concept of accretion disks originated from early binary star models, or from quasars observed in the mid-20th century. Some say it was the radio astronomers of the 1960s who first stumbled into the model, puzzled by the brightness of objects they couldn't fully see. Either way, once the idea clicked, everything changed. Suddenly, you didn't just have black holes, you had powered black holes. glowing, spinning, roaring black holes surrounded by death spirals of light. But let's get more tactile with this image, shall we? You drift alongside the disk now, parallel to its plane. You can feel the heat radiating off it, not through air since there is none, but as waves of electromagnetic fury. Your instruments, if they hadn't already melted, would be screeching from the intensity. Particles here collide at relativistic speeds, fusing and smashing and annihilating, producing cascades of radiation. And all of it spirals inward, tighter and tighter, tracing the black hole's gravitational grip like water circling a drain. And yes, there's turbulence, you better believe there's turbulence. The disk isn't smooth, it's chaotic. Variations in density create shockwaves and eddies. Magnetic fields twist the plasma into corkscrewing loops. As matter moves inward, it loses angular momentum, kind of like an ice skater pulling in her arms and spinning faster, and this process heats the material further, feeding the inferno. Here's your quirky tidbit. Accretion disks are loud. Not in the literal scream-through-space sense. Again, no sound in a vacuum, but in the electromagnetic sense. They roar across the spectrum, especially in X-rays, and when you convert those into sound waves for human ears, they produce eerie, low humming tones, like the universe is singing in its sleep but dreaming of supernovas. Now remember, this disk isn't just an isolated ring, it interacts with its surroundings. The intense radiation it emits can ionize gas in the nearby galaxy, causing vast clouds to glow. Winds driven by radiation pressure can push material away, creating loops and arcs of gas that dance like solar flares on a grand scale. And sometimes, the disk gets tilted, possibly from gravitational torques, maybe from the erratic way matter falls in, causing the whole structure to wobble and precess, like a record on a warped turntable. This wobble affects the jets too, making them swing and sway over time. Astronomers have observed jets that twist like garden sprinklers, sweeping across interstellar space and sometimes even smacking into nearby gas clouds. When that happens, it's like stirring milk into coffee. Eddies, turbulence, chaos, and occasionally star formation. Because nothing says new life like a jet of particles fired from a cosmic death spiral. Back to your perspective now. You're floating just above the disk's plane, watching the inner edge get narrower and brighter. At a certain point, mere kilometers from the event horizon, the disk reaches what's called the last stable orbit. Past this boundary, there are no safe paths. Matter here doesn't orbit anymore, it plunges, it dives straight in, accelerating, compressing, and finally slipping beneath the horizon, forever removed from the observable universe. And then, nothing. The light disappears, the matter is gone, and all that remains is the memory of its fall, encoded in the burst of energy it released on the way in. Here's a puzzle for the insomnia-prone. The inner edge of the accretion disk can vary depending on the black hole's spin. For a non-rotating black hole, the innermost stable orbit is about 3 Schwarzschild radii out, but for a maximally spinning black hole, the disk can get perilously close, just a hair above the event horizon. That means even more energy is extracted, even more light is released, and the jets, well, they get an extra kick. That's where this all starts leading. Jets. Jets don't just pop into existence like cosmic magic. They begin here, in this swirling madness. It's the combination of rotation, magnetic fields, and accreting matter that sets the stage. Magnetic field lines get pulled into the disk, twisted into towers of tension, like stretched rubber bands waiting to snap. As the field lines funnel toward the poles, they channel energy, raw, screaming, relativistic energy, upward. It's like squeezing a water balloon at both ends until jets of plasma shoot out the sides. Only instead of water, it's particles stripped of their electrons, moving at nearly the speed of light. And instead of a balloon, it's, well, a rotating monster made of space-time. You begin to rise now, pulled gently upward, just a few thousand kilometers above the black hole's axis of rotation. You can feel it. The magnetic fields, like stretched wires, humming with energy. Below you, the accretion disk blazes like a ring of fire. Ahead, barely visible at first, the base of the jet begins to form. It flickers, it pulses, it grows, and soon it will erupt. You hover above the poles now, balanced precariously in the invisible grip of magnetic field lines that stretch skyward like ghostly scaffolding. There's a peculiar silence here, not the absence of sound, which you've grown used to, but the anticipation of something about to happen. Below you, the accretion disk still spins like a carnival ride on fire. Around you, the space is thin, clean, strangely empty. But not for long, because this is where the mayhem begins. It starts with the magnetic fields. They're not calm, not organised, not politely following the rules. These are snarled, tangled ropes of energy, dragged into absurd shapes by the rotation of the black hole and the chaos of the infalling matter. As the black hole spins, it twists these magnetic lines tighter and tighter, winding them into loops and spirals that grow increasingly unstable. And like all good tension in the universe, it eventually demands release. That release takes the form of a jet, a narrow, focused beam of plasma and radiation that shoots out from the poles with unspeakable force. This is magnetic mayhem turned architectural. These jets aren't wide explosions, they're collimated like a fire hose on the tightest setting. Only, firing particles moving at nearly the speed of light. And the real kicker, these jets are powered by the black hole's rotation itself. This is the Blandford-Znajek mechanism. Named after two physicists who, in 1977, dared to ask, what if a spinning black hole could actually transfer its rotational energy into magnetic fields? What if those magnetic fields then launched jets straight into space? Turns out that's exactly what seems to happen. The idea is that magnetic field lines anchored in the accretion disk thread through the black hole's ergosphere, that twisted zone outside the event horizon where nothing can sit still. As the black hole spins, it drags those magnetic field lines around, winding them like springs, and like springs they push back. They create an electromagnetic torque that siphons energy right out of the black hole's spin. It's the most violent tug-of-war you can imagine, and the result is the formation of a jet. Historians still argue whether the Blandford-Znajek mechanism is the only way jets form. Other theories, like the Blandford-Payne process, yes, more Blandfords, suggest that the disk itself might also help launch the jet by flinging particles out along magnetic field lines, like beads sliding off a wire. Most likely it's a combo platter, multiple mechanisms working together to hurl plasma into deep space. But for you, standing metaphorically here near the jet's base, it's less about mechanisms and more about scale. This isn't a modest puff of particles. This is a column of light and matter so dense and so fast that it can travel millions of light years without breaking up. That's like aiming a laser pointer from Earth and hitting a marble in another galaxy. And these jets don't just shoot and fizzle, they last. Some of them are believed to remain active for millions of years, constantly fed by the disk's fury and the black hole's greed. The speed? Oh, just a hair under light speed. And because of relativistic effects, the particles in the jet don't just move fast, they act weird. They beam their radiation forward in a tight cone, like the universe's most focused flashlight. That's why, when we detect these jets from Earth, they sometimes appear brighter or dimmer depending on their angle. If the jet is pointed even vaguely toward us, it can seem far more luminous than it actually is, a phenomenon called relativistic beaming. And sometimes we see something even stranger, superluminal motion. That's when the jet appears to move faster than light. Of course, nothing can actually do that. But due to the way light travels and the angle of the jet's motion relative to Earth, it looks like it's outrunning itself. It's like a cosmic optical illusion, and we'll unpack that in more detail later, don't worry. For now, let's look at the anatomy of the jet itself. At the base, it's hot and dense, so packed with particles that light can barely escape. But as it moves outward, it cools and becomes more transparent, eventually radiating everything from X-rays to radio waves. Along the way, it can develop internal shock waves, where faster blobs of plasma overtake slower ones, slamming together and flaring brightly. These shocks are often what we detect from Earth, glowing like knots in a cosmic rope. Here's your quirky tidbit. Some jets wiggle. Not poetically, literally. Observations have shown that certain black hole jets aren't perfectly straight. They twist, bend, even spiral as they shoot outward. Why? Maybe the black hole itself is wobbling due to a recent galactic merger, or maybe the accretion disk is precessing like a tilted spinning top. In either case, the result is a jet that curves and sways like a drunken lightsaber. And what happens when these jets hit something? Oh, magic! When a jet slams into interstellar gas, it carves out vast bubbles, radio lobes the size of entire galaxies. It compresses material, stirs up magnetic fields, and sometimes triggers the birth of new stars. It's poetic, really. The violent breath of a black hole can lead to the gentle cradling of baby suns. But back at the core, near your imagined position, the view is hypnotic. You look down the length of the jet and it feels infinite. The particles move so fast that they seem to stretch space itself. You can't see individual atoms, of course, but you can see the glow. The jet pulses with synchrotron radiation, a kind of light produced when charged particles spiral through magnetic fields at relativistic speeds. It's that same eerie, polarized glow we see from distant galaxies and quasars. You wonder what would happen if you got inside the jet. Would you be vaporized instantly? Yes. Would time slow down? Sort of. Would you ride it across the galaxy like a sci-fi wormhole? Sadly no, but cool mental image. And then you remember, these jets aren't just scientific curiosities, they're useful. They help us find black holes we can't otherwise see. Long after the disk dims and the host galaxy fades, the radio lobes can remain, glowing like graffiti left by a long-gone party. Astronomers use these lingering signs to map the history of black hole activity across the universe. So next time you see a fuzzy radio image of a galaxy with two bright lobes on either side, know this: you're looking at the past violence of a black hole, written in the language of plasma and light. And to think, it all started here, with some magnetic mayhem. You're drifting now above the poles of the black hole, watching those luminous columns, those tightly coiled, screaming jets, begin to climb. And it's not just plasma shooting upward, it's structure, order, and physics flexing in ways that frankly shouldn't be allowed. If you could follow a single particle inside the jet, you'd watch it spiral along magnetic field lines like it was on a cosmic roller coaster, with no brakes, no seatbelt, and a view better than first class. Here's where the magic trick really begins. The jets, despite all their violence, remain remarkably focused. Not scattered, not exploding outward in every direction like some undisciplined fireball. No, these jets collimate, a fancy word for stay straight. They form narrow, stable beams, often for thousands or even millions of light years, like intergalactic pencils of light. That level of focus? Unbelievable. A laser pointer level of discipline scaled to galactic proportions. And the strange part? Much of that precision comes from the black hole's spin. The faster a black hole spins, the tighter it drags space-time around it. That twisted space-time doesn't just fling matter outward randomly, it sculpts it. You get these tidy jets shooting out from the poles because the black hole's rotation lines everything up. The magnetic fields, the plasma, the geometry of space-time itself, they all cooperate to produce something eerily symmetrical in the middle of absolute chaos. Historians still argue whether the exact role of spin in jet formation is fully understood. It's the hot gossip of astrophysics. Some believe spin is essential. No spin, no jet. Others think jets might form under certain conditions, even with slow spinning black holes, depending on the magnetic field configuration. But spin sure seems to supercharge the whole operation. And if there's one thing black holes love, it's power-ups. The jet climbs higher now, stretching away from the disk, and here's where it gets a little show-offy. Remember how we said the particles are moving at nearly the speed of light? That's true, but it gets better, or worse, depending on your stress level. To observers on Earth, these jets sometimes appear to be moving faster than light. Hold on, breathe. Don't throw your telescope out the window. This effect is called superluminal motion, and no, it doesn't violate Einstein's speed limit. It's a clever illusion caused by relativistic speeds and specific viewing angles. Picture this. The jet is aimed almost directly at you. As the particles emit light while racing toward us, the light from later moments in the jet's path arrives at Earth very soon after the earlier light. The jet appears to stretch, to leap, to move faster than light itself, when really it's just light playing tricks on your perspective, and we've seen this, repeatedly, in jets from quasars and microquasars, where the motion seems superluminal. It's one of the most satisfying paradoxes in modern astronomy. Nothing breaks the rules, but the illusion makes you question everything. Here's your quirky tidbit. Some scientists have compared black hole jets to cosmic flamethrowers, but with more in common with particle accelerators. In fact, the acceleration of particles within jets may produce some of the most energetic particles in the universe. Cosmic rays that slam into Earth's atmosphere, triggering showers of secondary particles. You could be hit by one right now, probably won't notice, unless you're a sensitive electronic system, in which case, sorry. Now let's get even stranger. Not all matter near the black hole gets ejected. Some particles hover. In theory, there's a narrow region above the poles where gravity and electromagnetic forces balance just enough that charged particles can remain suspended, trapped in a kind of magnetic limbo. It's temporary, sure, but it means some particles hang around before being swept into the jet or spiraling back down. This funnel wall region, as some theorists call it, is like the antechamber to jet formation. It's a holding zone for particles on the cusp of escape. Some even propose this region may serve as a natural accelerator, where particles bounce around in shock zones and magnetic reconnection events until they gain enough energy to join the jet's main flow. You watch as the jet narrows even further, collimated now into a beam just light days wide, even though it stretches for thousands of light years. The field lines surrounding it act like rails, keeping the particles from veering off course. It's astonishing that such structure can emerge from something so inherently violent. And it's not just electrons and protons. These jets often contain heavier ions, depending on what the accretion disk is feeding the black hole. Sometimes they even carry positrons, antimatter particles that, upon collision with regular electrons, annihilate in tiny bursts of energy. The jet is not only fast and focused, it's diverse, a veritable buffet of subatomic weirdness. And speaking of weirdness, let's talk about jet asymmetry. You'd think that since jets are launched from both poles, they'd look the same, but that's rarely the case. One jet might be longer, brighter, more structured. Why? Possibly because one side is pointed slightly more toward us, and relativistic beaming makes it look brighter. Or maybe it's because the environment around the black hole is uneven. One jet might be punching through dense interstellar gas, while the other is flying through emptiness. The universe doesn't do symmetry unless it absolutely has to, and all of this, every blazing particle, every radio lobe at the end of a jet, every twisted magnetic field, traces back to a paradox, something that doesn't emit light, producing the brightest objects in the cosmos. That's the joke. The one-liner the universe throws at us across billions of light years, because you've probably heard of quasars, those superluminous points of light from the early universe that confuse everyone by being brighter than entire galaxies. We'll dive deeper into them soon, but here's a spoiler. Their energy comes from black hole jets just like these, only bigger, older, hungrier. Back in your imaginary ship, you ride alongside the growing jet now, watching it stabilize. You're still close to the black hole, but the worst of the chaos is behind you. The field lines are stretching, the beam is focused, and the plasma is well on its way to being one of the brightest, most persistent features in the universe. And to think it all started from a disk of falling matter, shaped by gravity, sculpted by spin, and lit by electromagnetic fury. Darkness didn't just birth light, it organized it into a beam. Now hold that thought, because even small black holes can throw a tantrum. You follow the jet as it speeds outward, your virtual ship riding the edge of the beam like a surfer skimming the world's most aggressive tidal wave. The particles beside you are moving at over 99.9% the speed of light. That's not a poetic exaggeration, it's a physical reality, and because of that, you're about to experience one of the weirdest optical illusions the universe has to offer. Remember those jets we talked about seeming to move faster than light? Time to unpack that a little more, because this is where your sense of normal breaks down completely. It's called superluminal motion, and it's not just a glitch in the matrix. It's a predictable, observable phenomenon that occurs when objects move toward us at relativistic speeds, close to the speed of light, while also emitting light in our direction. Here's how the trick works. Let's say the jet shoots out a burst of plasma moving directly toward Earth, just slightly off from a perfect straight line. Because the particles are moving so fast, and because they're constantly emitting light along their journey, each photon they send out has less distance to travel to reach us than the one before it. The result? When we stitch those photons into a moving image, it appears as if the object is moving faster than light across the sky. You're not hallucinating, your brain isn't broken. But the universe is trolling you, just a little. Historians still argue whether this phenomenon was first noticed in the 1970s or earlier. Some of the earliest VLBI, very long baseline interferometry, radio observations revealed quasars with blobs of plasma seemingly moving faster than physics should allow. At first, people thought the data was wrong. Then they thought, oh no, we've broken causality. Eventually, the theory of relativistic beaming stepped in to save the day. Everyone calmed down. Mostly. What's even more disorienting is that these jets don't just look fast, they are fast. Maybe not faster than light fast, but enough to warp time and space around them in very real ways. From the perspective of the particles in the jet, time ticks normally. But to an outside observer, they appear compressed in time, beaming their light in a tight forward cone. Imagine holding a flashlight in a snowstorm, but the snowflakes are all racing ahead of you, and the beam sharpens into a pinprick. That's relativistic beaming. It means jets aimed even slightly toward us can appear dramatically brighter and more compact than they really are. Entire classifications of active galaxies, like blazars, are based on this effect. Here's your quirky tidbit. Some blazars fluctuate in brightness in just a matter of hours. That means the light-producing region must be tiny, light hours across maybe, yet we're seeing them from billions of light years away. The only reason they're visible at all is because the jet is aimed almost right at Earth, focused into a spotlight by relativistic effects. It's like the universe is holding a laser pointer right in your face from across the cosmos. Rude, but impressive. But let's not forget the reality beneath the illusion. These jets, no matter how fast they seem, are bound by the laws of physics. No individual particle breaks the speed of light barrier. What you're seeing is the result of time dilation, Doppler effects, and the angle of observation. It's the universe performing sleight of hand at 99.99% light speed. And this leads to another strange implication. Direction matters a lot. Two jets can be identical in speed, structure, and energy, but if one is pointed toward Earth and the other is pointed away, we'll see them very differently. One will appear blindingly bright, like a quasar or blazar, while the other might be virtually invisible. That asymmetry is purely due to the orientation of the system relative to us. Not because the jets are different, but because we are. Perspective, it turns out, is everything. A lesson both for astronomy and, frankly, Monday mornings. And here's a little bit of cosmic comedy for you. Despite all this beaming and relativistic motion and jet-launching chaos, we only ever see black holes indirectly. All the light, all the particles, all the superluminal weirdness. It's all coming from outside the event horizon. The black hole itself remains eternally visually silent. yet it's orchestrating the whole symphony. There's a term astronomers use when describing the way these high-speed jets emit radiation: synchrotron radiation. This happens when charged particles spiral through magnetic fields at near-light speed, emitting energy across the electromagnetic spectrum. The resulting light is polarized, meaning the waves align in specific directions, and that's something we can measure from Earth. By studying that polarization, we can actually map the magnetic field structure in and around these jets. It's kind of like listening to the static on a radio and figuring out what kind of antenna is broadcasting from 2 billion light years away. Nerdy? Absolutely. Cool? Beyond question. And speaking of nerdy, let's indulge a moment in cosmic scale. Some of the jets we observe, like the one from the galaxy Pictor A, stretch over 1.5 million light-years long. That's 15 times the diameter of the Milky Way. It's hard to even picture. If you put one of these jets in our galaxy, it would punch straight through the other side and keep going. From Earth, many of these jets are detected via radio waves. That's right. The very same technology that brings you late-night talk shows and overly enthusiastic commercials is also letting us peer into the hearts of active galaxies, watching plasma travel at speeds that bend reality. Makes you appreciate that dusty antenna on your roof just a little more, doesn't it? And here's the thing, these jets don't travel forever unchanged. As they move outward, they begin to interact with the intergalactic medium, the thin soup of gas and dust that fills the space between galaxies. That's where the real fun starts. Shock fronts, cooling flows, and the formation of massive radio lobes that balloon outward like the exhaust plumes of a rocket engine. We'll get to that soon. For now, you ride the jet a little longer, watching as the stream begins to cool, spreading gently at the edges but still blazing with energy at its core. Behind you, the black hole is shrinking into the distance, just a dark pit crowned by a luminous disk and those ever-twisting magnetic field lines. And ahead, well, ahead lies deep space, unbelievably empty, and yet full of ghosts. Cosmic rays, microwave background fuzz, wandering hydrogen atoms, and the aftershocks of galactic violence. You're watching something that started in the gravity well of a singularity travel outward to shape the structure of the cosmos. This isn't just a jet. It's a message, a trail, a signature in the dark, and we've only just begun to decipher it. Now don't get too comfortable floating alongside those million light-year-long jets, because while the supermassive black holes at the centres of galaxies often steal the spotlight, the smaller ones, they throw temper tantrums of their own. You're about to visit a far more intimate kind of chaos, the stellar mass black hole. These are the heavy remnants of once mighty stars. You know the kind, stars that burned bright, lived fast, and died in a spectacular gravitational collapse that would make most action movies feel under-budgeted. What's left behind is a black hole maybe 5 to 20 times the mass of our Sun. Smaller, yes, but not less dramatic. And just like their larger cousins, these stellar mass black holes also produce jets. You're probably wondering how something with less mass can still make those blazing beams. The answer? It's all about what's being fed into them. See, most stellar mass black holes we've detected aren't sitting out in space by themselves. They're in binary systems, paired with a normal star. And let's just say, it's not an equal relationship. You, dear observer, are now watching a scene unfold between one such pair. The star, a bloated, aging giant, drifts just a little too close to its black hole companion. Gravity doesn't even break a sweat. The black hole begins siphoning material off the star, stripping it like someone peeling the icing off a cake. That material spirals inward, forming, you guessed it, a hot spinning accretion disk. The scale is different, but the process is almost identical to what happens around supermassive black holes. The disk heats up, magnetic fields go berserk, and before long, jets form and shoot out from the poles. Historians still argue whether we fully understand how jets in these smaller systems achieve such high speeds. Some theorists suggest the spin of the black hole still plays a role. Others argue that the disk's turbulence and compact magnetic field structures can do the job on their own. Either way, the jets in these systems, often called microquasars, are no less dramatic for their smaller size. Yes, microquasars. The term might sound adorable, but these are not cute. You're now hovering near one called SS433, one of the most studied microquasars in our galaxy. It's jets. They move at about 26% the speed of light. That's not just fast, that's lose track of decades in a blur of particles fast. And to make things even more ridiculous, the jets precess, meaning they swing around like a lawn sprinkler slowly tracing out a cone in space. Every 162 days, the orientation of the jets completes a full wobble, and the results are both beautiful and mind-bending. And here's your quirky tidbit. When astronomers first observed SS433's shifting emission lines in the 1970s, they thought their instruments were broken. The Doppler shifts were so wild that they didn't make sense. But once the precession model was introduced, boom, microquasar confirmed. The instruments were fine, it was reality that needed adjusting, and SS433 isn't alone. Another infamous microquasar is GROJ 1655-40, sometimes nicknamed the Mini Blazer. It's also in a binary system, also accreting matter, and it produced superluminal motion. Again, the jet appeared to move faster than light, thanks to its angle and speed. This kind of behaviour shows just how universal the jet phenomenon is. Whether you're dealing with a black hole the size of a city, or one that could swallow the solar system whole, the same physics applies. Gravity pulls in matter, the disk forms, magnetic fields snap into place, jets erupt, the scale changes, the environment changes, but the underlying mechanics are weirdly consistent. Even in these microquasar systems, the jets can influence their surroundings. They blow bubbles into the interstellar medium, carve shock fronts, and heat nearby gas. It's like watching a toddler with a fire hose. The mess is smaller, but just as dramatic when you're standing nearby. Now here's where things get particularly cool and messy. These microquasars don't run 24/7. They flicker. They switch on and off depending on how much material they're accreting at any given time. Sometimes the black hole is starved. The disk cools, the jets vanish. Other times the star feeds more mass into the disk and boom, the system lights up again in radio and X-ray bands, with jets screaming back to life like they never left. In fact, some of these systems are cyclic. They flare, they calm down, they flare again. Watching them over months or years is like observing a celestial mood swing. One moment, silence. The next, full-blown particle eruption. It's temperamental, unpredictable, and completely delightful for astronomers trying to decode the pattern. And here's a little fringe nugget. Some scientists think that watching microquasars in real time gives us a glimpse into how supermassive black holes behaved in the early universe. Since the physics is similar, but the timescales are much shorter, hours or days instead of millions of years, these smaller systems let us observe an entire jet cycle in a human-friendly time frame. Kind of like studying lab mice instead of elephants. There's even a potential connection between microquasars and gamma-ray bursts, those brief but absurdly bright flashes we detect from distant galaxies. Some gamma-ray bursts are thought to result from stellar mass black holes forming during supernovae, jets forming in real time as the core collapses. But we'll save that drama for later. Right now, just picture this. A star, quietly orbiting in the void, suddenly begins shedding its atmosphere into a disk. That disk flares, jets erupt, and particles are launched across space faster than almost anything else in the galaxy. And yet, to the naked eye, nothing. Most of these systems are too small and too faint to see without special instruments. But if your eyes could see in X-rays or radio waves, you'd witness tiny fireworks of cosmic fury going off all across the sky. The galaxy is full of these binary systems. We've catalogued dozens, maybe hundreds, and suspect thousands more. They're hiding behind dust clouds, inside dense star fields, quietly blasting jets and giving away their secrets to any telescope patient enough to listen. So next time you think black holes are only big, lumbering monsters at the hearts of galaxies, remember, even the little ones have a flair for dramatic exits, especially when they find a companion star with a few too many layers to spare. And speaking of galactic drama queens, up next, the quasars. The further you drift from the cozy chaos of stellar mass black holes and their tantrum-throwing microquasars, the more you begin to sense it. A cold, ancient light whispering through the darkness. You follow it across billions of light years, and there, like a cosmic lighthouse blinking from the edge of time, it appears a quasar. Now, let's set the scene. It's the early universe. Galaxies are just getting their act together. Stars are forming in wild, untamed clusters. There's dust, gas, turbulence, and right in the centre of it all, a black hole, billions of times more massive than the Sun, doing what black holes do best, eating everything. But this one, it eats with style. Gas and dust spiral inward at a staggering rate, feeding the black hole faster than most ever get the chance to. The accretion disk reaches extreme temperatures, magnetic fields get supercharged, and the result? A jet of particles and radiation so intense it can be seen across the visible universe. That, friend, is a quasar, a quasi-stellar object, so named because it looked like a star in early observations but packed the brightness of an entire galaxy. And yes, it's powered by a black hole that technically isn't even visible. Welcome to one of the biggest cosmic paradoxes. The brightest objects in the universe are created by something that emits no light of its own. Historians still argue whether the first quasar, 3C273, was properly understood when it was discovered in 1963. The light it emitted had a redshift so extreme that it suggested it was more than 2 billion light-years away. People scratched their heads. How could something that far away be that bright? For a while, some scientists proposed bizarre star-like objects in our galaxy as an explanation, but nope. The only solution that fit was terrifying and elegant, a supermassive black hole gobbling matter in the early universe. And as you float now beside one, you can barely look at it. The light from the accretion disk is overwhelming. The jets extend in both directions, blasting outward into the cosmic fog. The central region, the so-called active galactic nucleus, glows in every wavelength imaginable: radio, infrared, ultraviolet, X-rays and gamma rays. It's not just bright, it's alive. A furious engine of energy radiating into the void. Quasars are more than just flashy lights. They're history books. Because of their extreme brightness, we can see them at vast distances, which means we're seeing them as they were billions of years ago. They're the streetlights of the young universe, revealing where galaxies were actively forming, colliding, growing. Their jets and radiation influenced how gas was distributed across intergalactic space. Some may have even shut down star formation in their host galaxies by heating or blowing away the cold gas needed to make new stars. Imagine shining a blowtorch inside a nursery. That's what a quasar jet can do to a galaxy. And here's your quirky tidbit. Some quasars flicker, not like a candle, more like a faulty stadium spotlight. Their brightness can change on timescales of months, sometimes even days. That tells us something important. The region emitting that light must be small. If a quasar's brightness changes over 2 days, the region responsible can't be larger than 2 light days across. That's teeny tiny, cosmically speaking, roughly the size of our solar system, and yet it outshines hundreds of billions of stars. Let's zoom out a little. Quasars are just one type of active galactic nucleus, AGN. These are galaxies with unusually energetic centres, typically powered by accretion onto a supermassive black hole. The exact classification, quasar, blazar, Seyfert galaxy, radio galaxy, depends on a few things: the orientation of the jet, the brightness of the host galaxy, the wavelengths we observe, and just how energetic the whole system is. If the jet's aimed almost directly at us, we call it a blazar, and we'll get to those dramatic little attention seekers later, but quasars are the showboats of the early universe. The further back we look, the more quasars we find. That's because in the early universe, gas was abundant and galaxies were smaller and more chaotic. Ideal feeding grounds for supermassive black holes. Over time, many quasars went quiet as the gas ran out or stabilized. The black holes didn't go away, they just stopped glowing. That means the galaxies you see today, quiet, mature, full of stars and spiral arms, could very well be the graveyards of old quasars. Their central black holes still lurk there, enormous and invisible, but no longer surrounded by enough food to light up the night sky. Kind of sad, kind of awesome. Now here's a fun bit of cosmic recycling. Those same black holes could flare back to life if something disrupts the calm. Say, a galaxy merger. Suddenly you have fresh gas funneled to the core, a new accretion disk, and voila, your dead quasar wakes up like a dragon rolling over in its sleep. We may even be seeing this in real time with some changing look quasars, systems that brighten or dim dramatically over just a few years. No one's sure exactly why. Maybe the accretion rate changed, maybe the disk got disrupted, maybe black holes have moods, we're still working on it. And let's not forget the jets. Quasars often launch the most powerful jets we've ever seen, narrow beams of relativistic particles stretching for hundreds of thousands of light years, sometimes more. These jets are visible in radio wavelengths, and their ends flare into giant lobes as they slam into intergalactic gas. You're watching feedback on the grandest scale possible. Energy from the black hole shaping the very structure of the galaxy and its surroundings. In some cases, these jets punch through their host galaxies, blowing holes in star-forming regions and leaving trails of heated gas behind. It's cosmic landscaping by particle cannon. And it tells us something important. Black holes aren't just passive consumers of matter, they're architects, shaping galaxies, regulating star formation, maybe even influencing how cosmic structure forms on the larger scales. So when you look at a quasar, you're not just seeing a glowing dot in the sky, you're seeing a stage of galactic evolution, a phase that many, maybe most galaxies pass through as their central black holes gorge on matter and vomit jets into space. And even though we're seeing many of these objects as they were billions of years ago, they're still influencing us. Their light, their jets, their remnants. They reach us today, crossing unimaginable distances to let us piece together the story of cosmic growth. You float a little farther now, away from the screaming heart of the quasar, into the quieter edge of its host galaxy. The stars are dimmer here, the gas thinner, but still, the memory of that central engine lingers, like an afterimage burned into your vision. Quasars don't just shine, they sculpt, they disrupt. They remind us that even darkness, given the right conditions, can outshine everything around it. And now, if you're ready, let's watch what happens when these jets start shaping galaxies themselves. You drift further outward now, letting the glare of the quasar fade behind you as the jets extend into the intergalactic dark. But their influence is far from over. In fact, this is where the story of black hole jets takes an unexpectedly creative turn, because far from being just flashy particle cannons, these jets sculpt galaxies. Yes, really. It turns out these twin streams of radiation and plasma aren't just the black hole's high-speed tantrums. They're tools, chisels carving interstellar gas, reshaping galactic structure, and sometimes even igniting star formation in the aftermath of their violent passage. You're watching the black hole do more than feed or destroy. You're watching it build. Let's break it down. Every galaxy needs gas to make stars, but this gas isn't neatly arranged like ingredients in a recipe. It drifts, it clumps, it cools slowly. In many galaxies, especially younger or more active ones, much of this gas is stuck in the halo or floating uselessly in the outer regions. The problem? It's too hot, or too diffuse, or too disorganized to collapse into stars. Enter the black hole jet. These jets rip through galactic environments like high-pressure hoses, compressing some clouds, heating others, and in the process, either kickstarting or shutting down star formation, depending on where they go and what they hit. This dual behaviour, both destructive and creative, is part of what astronomers call AGN feedback, and it might just explain why galaxies grow the way they do. You're now watching a jet slam into a gas cloud the size of a small solar system. The shock wave compresses it, pressure rises, the cloud collapses, a new star is born, possibly many. This is called positive feedback, and though it's rarer than the alternative, we have evidence it happens, especially in certain radio galaxies. But turn your head just slightly, and you'll see the flip side. A second jet carves through another region of the galaxy and blows away the cold gas entirely. It heats it, ionizes it, scatters it into the void. This gas won't form stars anytime soon. It's now part of a long, lonely outflow drifting through intergalactic space. That's negative feedback, and it's more common. In fact, many modern galaxies are probably quieter today because of it. This might sound counterintuitive. Why would the universe hand galaxies a powerful engine, only to have it slow down their star-making potential? Well, it's about balance. If galaxies formed stars unchecked, they'd burn through their gas too quickly. They'd shine too bright too soon and fizzle out like fireworks. But thanks to black hole feedback, the process slows. Star formation becomes more regulated. Galaxies evolve over billions of years instead of just a few million. In other words, jets help stretch the cosmic timeline. Historians still argue whether AGN feedback alone is enough to explain galaxy quenching, the mysterious process where a once star-forming galaxy suddenly goes quiet. Some say jets are the key. Others point to environmental factors, like galaxy collisions or interactions with hot cluster gas. It's probably a bit of everything, but jets are too powerful to ignore. Now here's your quirky tidbit. One galaxy, nicknamed the Teacup Galaxy, features a visible outflow from its central black hole that, when imaged in radio wavelengths, resembles the steam rising from a kettle. This elegant little metaphor hides a fierce reality. The gas in the steam is being blasted out at thousands of kilometers per second. A gentle teacup, it is not. Let's get more visual. You're flying above Hercules A, a giant elliptical galaxy located about 2 billion light-years away. Its central black hole launches jets that extend for more than 1 million light-years in either direction. At the ends of those jets, enormous radio lobes, ballooning regions of glowing particles formed as the jet slams into intergalactic gas, loses speed and puffs outward like smoke hitting a wall. These lobes glow in radio frequencies for tens of millions of years after the central engine goes quiet. They're like cosmic footprints, showing where energy once passed and left its mark. Inside them, magnetic fields twist and decay. Particles cool and radiate away their energy. But they still whisper the story of the black hole that launched them. This is legacy. Jet-powered legacy. Even more amazing. Some galaxies have double sets of radio lobes, so-called X-shaped radio galaxies, which may indicate that the black hole's axis shifted over time, perhaps due to a galaxy merger. The original jets faded, the black hole reoriented, and new jets launched in a different direction. The result is a giant X-shaped emission pattern, written in plasma across space. And yes, it's as epic as it sounds, but jets don't always travel freely. In denser galaxies or galaxy clusters, they can get bent, twisted, even reversed. Sometimes they form head-tail radio galaxies, where the jet appears to trail behind the galaxy like a windswept ribbon. That happens when the galaxy is ploughing through a cluster, and the surrounding gas pushes back against the jet's forward momentum. Picture a fighter jet moving through thick air, its exhaust plume trailing and bending as it moves. The universe is full of these interactions, jets smacking into things, bouncing off dense clouds, or being redirected entirely. Each event leaves a signature, a shape, a structure that astronomers can study to piece together the history of both the black hole and the galaxy it lives in. And here's something especially poetic. In some cases, the impact of a jet doesn't just shape gas, it sculpts galactic structure. Spiral arms, gas rings, central voids, all of these can be influenced by the presence of a jet or the feedback from earlier AGN activity. It's as if the black hole is holding a chisel, slowly carving the shape of the galaxy from the inside out. And to think, it's doing all this while staying completely invisible. You look back now at the path the jet has carved. In its wake, bubbles, voids, glowing lobes, and trails of disrupted gas. What started as a narrow beam of plasma has become a tool of galactic engineering. This isn't just violence, this isn't just a tantrum, this is feedback. And without it, the galaxies we see today wouldn't exist in their familiar forms. So the next time you see a picture of a serene spiral galaxy, or a majestic elliptical floating in space, remember, somewhere deep in its past a jet may have roared, carved, or silenced the very stuff that makes stars. And now, let's dig into the argument that still fuels conference rooms and Reddit threads alike. Just where do these jets come from? So, you've seen the jets form. You've followed them from their violent birth in an accretion disk to their long sculpting journeys across galaxies. You've watched them heat, carve, and even create. But now the question rises, one that divides astrophysicists, sparks heated debates, and occasionally leads to very passive-aggressive PowerPoint slides at astronomy conferences. Where exactly do these jets come from? Because while we've got the broad strokes, black holes, spinning disks, magnetic fields, the fine print remains frustratingly elusive. You'd think that after decades of staring at these things across the cosmos, we'd have nailed down the launch mechanism, but nope. The universe, once again, serves the mystery with a smirk. So, let's dig into the great debate. What's the actual engine that powers a black hole jet? There are three main suspects, and like any good cosmic whodunit, each has motive, means, and a few puzzling plot holes. Suspect number 1, the accretion disk itself. This theory says the disk does it all. As material spirals inward, it heats up and generates chaotic magnetic fields. These tangled fields twist, reconnect, and explode outward in a process known as magnetic reconnection, a kind of cosmic snapback that launches particles up and out. The energy comes from the inflowing material itself. The more stuff you dump into the disk, the stronger the fields become, and the harder the system spits matter out of the poles. This idea is supported by a similar phenomenon we see in young stars, which also produce jets via accretion disks. If protostars can manage it without needing a singularity at their core, maybe black holes don't need anything fancy either, just a spinning messy disk and a good set of magnetic field lines. Suspect number 2, the spinning black hole, aka the Blandford-Znajek mechanism. You've heard this name before, and for good reason. This mechanism proposes that the spin of the black hole itself is the fuel source. As the black hole rotates, it drags spacetime around with it, like a cosmic egg beater. If magnetic field lines pass through the black hole's ergosphere, the twisted zone of spacetime just outside the event horizon, they get wound up and can extract rotational energy directly from the black hole. Imagine a turbine, except the turbine is a spinning pit of doom, and the power it releases shoots matter into intergalactic space. Neat. This theory has serious traction in the community because it provides a way to launch jets, even when the accretion disk isn't particularly active. Some AGNs have weak disks but powerful jets, suggesting the black hole's spin might be doing the heavy lifting. But of course, not everyone agrees. Suspect number 3, the marriage of both. Why choose one when you can have both? This hybrid theory suggests that the disk provides the initial scaffolding, the magnetic fields, the raw material, and the spin of the black hole supercharges it. Think of it like a campfire. The disk is the wood, the spin is the gasoline. Together they create the most violent plasma flamethrower in the known universe. In this model, the accretion disk feeds magnetic field lines into the ergosphere, where they get twisted by the black hole's rotation and launch jets. It's a team effort, if a somewhat messy one. Historians still argue whether the Blandford-Znajek model has ever been definitively confirmed. Some simulations support it. Others suggest the disk's magnetic fields could be enough on their own, and then there's observational data, which often leaves just enough ambiguity to keep everyone disagreeing over lunch. Here's your quirky tidbit. Some researchers have built analog models of black hole jet mechanisms using fluid tanks, magnets, and yes, even bathtubs. These hydrodynamic experiments attempt to mimic the way magnetic fields might behave near spinning objects. Do they capture the full complexity of relativistic astrophysics? Absolutely not. Are they entertaining and occasionally insightful? You bet. Now let's talk about magnetically arrested disks, a phrase that sounds like an interstellar court drama, but actually refers to a real phenomenon. In some black hole systems, the inflowing gas brings in so much magnetic field that the field becomes too strong. It starts to choke off further accretion. The disk can't feed the black hole as easily anymore because the magnetic pressure pushes back against the inflowing gas. But that built-up magnetic field, it's perfect for launching jets. These systems are believed to produce the most powerful jets observed precisely because of this magnetic bottleneck. If you're imagining a blocked pipe under pressure suddenly blowing its top, you're on the right track. Simulations of these systems show beautiful structures, jets forming as narrow, stable funnels threaded with magnetic field lines, and turbulent disks swirling around the base. But those same simulations often depend on tricky assumptions: idealized plasmas, symmetrical systems, or simplified relativistic effects. The universe, as you've probably guessed by now, is rarely that polite. Observationally, we're starting to chip away at the mystery. In 2019 and 2021, the Event Horizon Telescope captured polarized light from the black hole in galaxy M87. This polarization traces the magnetic field lines near the event horizon, giving us direct evidence that strong magnetic fields are indeed at work, possibly just as the Blandford-Zanaev mechanism predicted. Still, the debate rages. Some argue the resolution isn't high enough. Others point out that we're still relying heavily on simulation interpretations. A few brave souls even whisper that we might be missing something fundamental about jet formation, something beyond our current models. And honestly, that might be true, because at the heart of this whole debate lies something profound. We're watching invisible forces shape galaxies, create radiation that crosses the universe, and fire particles at energies no earthly collider can reach, and yet we still don't fully understand how. That's both humbling and thrilling. The mystery isn't a flaw, it's the point. You look now at a black hole's pole, imaginary in your mind's eye, and you see the possibilities. The disk swirling, the magnetic field stretching, the space-time bending, the jet just about to erupt. And somewhere in that complex ballet of energy and gravity, the launch mechanism lies. Maybe it's the spin, maybe it's the disk, maybe it's a symphony of both, tuned to the frequency of madness. But whatever it is, it turns darkness into light, silence into motion, and theory into an open question that won't let us sleep. Good thing you're already here for the bedtime story. Up next, we watch what happens when the jet stops. You've seen the jets form, narrow, radiant pillars of fury forged from spin, magnetism, and matter, pushed to the brink of physical law. But even the most unstoppable beams don't blaze forever. Everything, eventually, must quiet. And that includes the black hole. You now drift near a galaxy that once blazed with a quasar at its core. You can tell because the afterglow is still painted across the sky, radio lobes stretching like bruises across intergalactic space, faded but unmistakable. But if you look at the centre, nothing. No glowing disk, no beams of plasma, no drama. It's gone silent. And that, in many ways, is more haunting than the fire. Welcome to the off switch, when black holes stop feeding and their jets vanish into the quiet dark. Black holes are not constant engines. They don't run on forever like cosmic furnaces. Their activity depends entirely on what's around them, and more importantly, what's falling in. No food, no disk, no jets. It's a fragile system, really, for something so dramatic. There are many reasons a black hole might stop shining. The the accretion disk may run out of gas. The host galaxy might stabilize, no longer funneling material toward the center. Or another galaxy might have collided and stolen the food supply. The universe is full of thieves. When this happens, the accretion disk fades, sometimes dramatically so. The light dims, the X-rays cut off, and those towering jets, they sputter and vanish. What was once a cosmic lighthouse becomes a black hole again. Just a gravitational well, silent and invisible. Historians still argue whether all galaxies with supermassive black holes go through active phases, or if some black holes are born quiet and stay that way. The truth may lie somewhere in the middle. Perhaps every black hole has the potential to flare, but only those in turbulent environments get the chance to light up. And here's your quirky tidbit. Some galaxies may cycle in and out of active states over and over, flaring up for a few million years, going dormant for tens of millions more, and then flaring again. They're like cosmic lighthouses with long, erratic blink cycles. If you have the patience to wait a few million years. Let's bring in a real-world example, the galaxy IC 2497. This was once a bright quasar. We know this not because we can see it now, it's currently quiet, but because of what's called Hani's voorwerp. Yes, really. It's a glowing green cloud discovered by a Dutch schoolteacher named Hanny van Arkel in 2007 while participating in a citizen science project. This glowing blob sits tens of thousands of light years away from the galaxy's centre, but it's still fluorescing with the afterglow of ionizing radiation from the black hole as it was tens of thousands of years ago. That means the black hole was active then, but has since gone quiet. Hani's voorwerp is literally a light echo, a ghost. You float now in one such ghost zone, a region where the radiolobes still hum, the X-rays still scatter, but the core is silent. The jet stopped, but its footprint remains, a fossilized beam frozen in space. So how fast can a jet stop? Faster than you might think. Some jets fade gradually as the fuel trickles out. The disk dims slowly. The energy flow narrows, cools, and finally vanishes. But others? They cut off fast, as in within years. That's rare, but we've seen it. These so-called changing-look AGNs can switch from blinding quasars to quiet cores on human timescales. And no, we don't totally know why. It could be a sudden drop in the accretion rate, it could be obscuring clouds passing in front of the core, or it could be the magnetic field structure collapsing, like scaffolding giving way. Whatever the cause, the jet stops. And when it does, the lobe structures at the end of the beam begin to fade, not instantly, but over millions of years. You're now observing one of these fading lobes. It's still glowing in radio light, still detectable, but it's like watching smoke slowly thin in the wind. The high-energy particles begin to decay, the magnetic fields start to dissipate, synchrotron radiation declines. The once sculpting jet becomes an echo. The galaxy goes back to business. Stars keep forming or they don't. Spiral arms twist quietly. And at the centre, a black hole, no longer hungry. Here's something to think about. We've found many massive galaxies with dormant black holes at their cores, silent, invisible. But the only reason we know those black holes are there is because of the stars orbiting them. Their motions betray a mass that can't be seen. No light, no flare, just gravity. It's like catching a ghost by watching the way the curtains move. The Milky Way's own central black hole, Sagittarius, a star, is mostly quiet now. But there's evidence it was active in the past. Fermi bubbles, giant balloon-like structures above and below the galactic plane, may be the remnants of a jet or outflow that occurred millions of years ago. It's sleeping now, but it remembers. And sometimes they wake up. A passing cloud of gas, an infalling star, a galactic collision, and suddenly the black hole has a new buffet. The disk reforms, the jets reignite, and what was silent becomes a cosmic scream once again. This cyclical behaviour means jets are not just events. They're episodes in the life of a galaxy, periods of flare and silence, of carving and resting, of light and dark. Some astrophysicists have even proposed that every galaxy with a central black hole goes through these phases, like seasons, active, passive, reborn. Each jet is a signature not of destruction, but of transformation. And when they stop, they don't leave silence, they leave structure, they leave clues, they leave stories, waiting to be read in the faint glow of leftover radio waves. You hover now near one of these fossil jets. You trace its path back to the galactic core. You see no light, no motion, no disk, just a dark centre, an old engine, a memory. But deep inside, the black hole waits, patient, hungry, capable of turning darkness into light again and again. And just when you think jets are a black hole exclusive, along comes a neutron star with something to prove. You're floating now in a pocket of space far from any galaxy's bright centre, a quiet corridor of the cosmos where things seem calm until they're not. Suddenly a flash, a focused beam of radiation streaks out from what looks like a faint flickering star. But hold on, that's not a black hole. It's a neutron star, one of the universe's other great overachievers in the category of incomprehensibly dense things that make dramatic exits. And yes, it just launched a jet. Surprise. For all the reputation black holes have earned for their elegant chaos and light-eating tendencies, they're not the only cosmic engines capable of hurling matter across space like it owes them money. Under the right conditions, neutron stars, especially a special class called pulsars and magnetars, can produce powerful, collimated jets too. So how does a dead star with a crust manage to mimic a jet-spewing singularity? Let's start at the core. Neutron stars are what's left when a star dies but doesn't quite collapse all the way. A supernova goes off. The outer layers of the star get blasted into space, and the core implodes into a sphere about 20 kilometers across, packing more mass than the sun into something the size of a city. These things are so dense that a single teaspoon of neutron star matter would weigh around 1 billion tons. That's not ideal for breakfast. Now, most neutron stars don't launch jets, but the ones that accrete matter from a nearby companion star, or those born spinning rapidly with intense magnetic fields, can build up the right ingredients. Sound familiar? Yep. A neutron star with a strong enough magnetic field, spinning fast and accreting material, can form an accretion disk just like a black hole. And with that disk comes turbulence, magnetic chaos, plasma, and in the right geometry, a jet. Historians still argue whether neutron star jets operate under the same exact physics as black hole jets, or whether the surface, the existence of a surface, changes the game. After all, black holes have no edge. Anything falling in passes through the event horizon. But neutron stars have crusts, solid, terrifying crusts. Matter falling onto a neutron star crashes into that surface, releasing bursts of X-rays in the process. And yet, jets still form. Somehow. Here's your quirky tidbit. In the early 2000s, a source called Scorpius X1 was confirmed to produce relativistic jets, and it's a neutron star. That made it the first non-black hole system with confirmed jet activity, shocking many who had assumed jets were a black hole-only party trick. Since then, several other neutron star X-ray binaries have been observed producing jets, especially during specific phases of their accretion cycles. Like black holes, they go through states: quiet, active, bursting, and the jets tend to emerge during the transitions, when the disk is unstable and magnetic fields are reorganizing themselves into launch-ready configurations. But there are some big differences. For one, neutron star jets tend to be weaker than those from black holes. That's likely because the neutron star's surface absorbs some of the energy that would otherwise go into launching a jet. In black holes, all infalling energy crosses the event horizon, disappearing forever. There's no surface to get in the way. Still, neutron star jets can reach speeds up to 0.7 times the speed of light. That's not quite quasar level, but it's more than enough to create lobes, produce synchrotron radiation, and occasionally fool astronomers into thinking they're looking at a microquasar, until they look closer. And then there's the neutron star's trump card, its magnetic field. Most neutron stars already have magnetic fields trillions of times stronger than Earth's, but magnetars crank that up by several orders of magnitude. These are neutron stars with magnetic fields so strong they can literally shift the atoms in nearby matter. We're talking about magnetic power that would tear your credit cards apart from across the solar system. Though magnetars don't usually produce jets in the traditional sense, they do emit intense bursts of radiation, some of which are narrowly beamed and could be jet-like in structure. In 2004, a magnetar in our galaxy sent out a gamma-ray flare so powerful it briefly ionized Earth's upper atmosphere, even from 50,000 light-years away. Let that sink in. A neutron star sneezed, and our planet's atmosphere blinked. More recently, there's growing evidence that fast radio bursts, FRBS, those millisecond-long flashes of radio waves coming from deep space, might be tied to magnetars. Some researchers suggest that these could be highly collimated emissions, possibly involving small-scale jet-like behaviour. It's still speculative, but it's yet another way these crust-covered corpses are mimicking their jet-flinging cousins. But here's the real kicker. Sometimes we find systems, like CRX-1 or IGRJ 18245-2452, that blur the lines so well between black hole and neutron star jets that the only way to tell the difference is by looking for a signature from the surface. If you detect a burst, a kind of thermonuclear explosion on the neutron star's crust, you've got confirmation that it's not a black hole. Jet? Check. Accretion disk? Check. Giant burst of X-rays caused by matter hitting a solid surface? Ah, there's your giveaway. So what does this all mean? It means that jet physics might not belong to black holes alone. It might be a broader feature of accreting compact objects. It might not matter if there's a surface or an event horizon, as long as you have a strong gravitational pull, a fast spin, a chaotic accretion disk, a magnetic field's gone rogue. Put those together, and the universe seems to love launching stuff into space at nearly the speed of light. You float now beside a neutron star watching it flicker and breathe. Its crust is covered in scars from infalling matter. Its magnetic field arcs out into space like invisible lightning, and from its poles, a focused jet. Faint but definite, spiralling outward with purpose. Not as bright, not as long, not as loud, but a jet nonetheless. It makes you wonder, maybe the jet isn't about the black hole at all. Maybe it's about what happens when matter spins, falls, and tries to organize itself against chaos. Maybe the universe just loves a good outflow, and just when you're thinking you've seen the limits of high-speed plasma, something explodes, violently, briefly, and with enough energy to put entire galaxies to shame. Yeah, it's time we talked about gamma-ray bursts. You barely have time to react before the darkness ahead ruptures. A blinding flash cuts across space. Not slow and graceful like a jet, but sudden, sharp, and furious. For a few glorious seconds, it's the brightest thing in the universe. And then, it's gone. But the aftershock lingers, even from light years away. You weren't just witness to a cosmic flashbulb. You saw a gamma-ray burst, a GRB for those in a hurry. And friend, this isn't just jet behaviour. This is jets on overdrive. GRBs are the universe's most dramatic final acts. If black holes are quiet monsters and quasars are drama queens, GRBs are full-blown rock stars trashing the stage and exploding the stadium on their way out. And yes, they involve jets. Let's rewind. There are two main types of gamma-ray bursts. First, long GRBs, those that last from about 2 seconds up to several minutes, a luxurious eternity by gamma-ray standards. These are thought to come from the collapse of massive stars, hypernovae. When these stars die, they don't just go supernova, they implode, forming a black hole in a split second. As the star collapses, a disk of infalling material forms around the newly born black hole, and that disk immediately fires a pair of narrow ultra-relativistic jets out of the poles. These jets slam through the outer layers of the collapsing star, emerge into space, and blast gamma rays across the cosmos. If the jet is pointed even vaguely in your direction, congratulations, you've just been gamma rayed. Historians still argue whether GRBs were first detected intentionally or by complete accident. Spoiler, it was an accident. Back in the late 1960s, US satellites designed to detect nuclear weapons tests picked up something odd. Bursts of gamma radiation coming from space, not Earth. It wasn't long before astronomers realized something out there was exploding hard. Here's your quirky tidbit. These satellites, called Vela, weren't even supposed to be doing astrophysics. They were peacekeeping spies that accidentally stumbled into some of the most powerful explosions the universe has ever cooked up. Now, for the short GRBs, those lasting less than 2 seconds. Don't be fooled by the name. These are just as intense. They're believed to come from the collision of 2 neutron stars, or a neutron star and a black hole. When these dense remnants spiral into each other, they create a brief, sharp burst of gamma rays, followed by the formation of a new black hole. And yes, you guessed it, a jet emerges here too. You're hovering now above one such collision site moments before the event. 2 neutron stars dancing a deadly waltz, their orbits shrinking as they radiate away energy as gravitational waves. When they merge, they release more energy in a single second than the Sun will emit in its entire 10 billion year lifetime. The jet that forms is narrow, often just a few degrees wide, and moving at over 99.9999% the speed of light. That's not a typo. This is relativistic motion taken to its limit. And from Earth, if we're lucky enough to be in the beam's path, we detect a sharp, sudden spike in gamma rays, followed by a fading glow in X-ray, optical and radio light. That fading glow is the afterglow, as the jet slams into surrounding gas and slows down, radiating energy across the spectrum. In 2017, for the first time, astronomers detected both gravitational waves and a short GRB from the same event, GW 170817. It was the merger of 2 neutron stars in a galaxy 130 million light-years away. Not only did we hear the merger through space-time ripples, but we saw the jet emerge afterward, an enormous breakthrough for multi-messenger astronomy. And it proved something big. GRBs are real-time jet births. They're the ignition of a brand new black hole or a hypercompact neutron star, and the jet they launch is powerful enough to light up the universe. But here's where GRBs get weird. Because of how focused the jet is, we only detect a tiny fraction of the ones that occur. If the beam isn't pointed toward Earth, we miss it entirely. Some estimates suggest that for every gamma ray burst we see, dozens more happen out of view. You might say the universe is bursting with GRBs. We just don't get the invite. And there's still more mystery. For example, we don't fully understand how the jets form so quickly. In both long and short GRBs, the time between black hole formation and jet launch is measured in milliseconds. That means the engine revs up almost instantly. Simulation suggests that extremely strong magnetic fields and intense rotation play a role, possibly a version of the same Blandford-Znajek mechanism we've seen with black holes. But this time, the stakes are higher, the speed's greater, the environment explosive. Some theories even suggest a baryon-free fireball, a nearly pure energy jet launched at near-light speed, which then picks up particles and becomes visible as it plows into surrounding gas. These jets are so fast and so clean that they can't tolerate excess mass. If too much material blocks their path, no GRB, no jet. And sometimes that happens. We think many massive stars die quietly without GRBs because their jets get choked, trapped inside the stellar envelope, never escaping. In those cases, the black hole forms, but the energy stays bottled up. You float now at a respectful distance from a GRB afterglow, watching as the light fades. The initial flash is gone, but what remains is a glowing ember of radiation moving through space, cooling, scattering, and eventually merging with the cosmic background. Even at this distance, the power is humbling. You imagine one going off in the Milky Way, maybe within a few thousand light years. If it were pointed at Earth, the high-energy radiation could strip away our ozone layer in seconds. Some scientists even propose that past mass extinctions might have been caused by distant GRBS. The fossil record, after all, doesn't come with timestamps for gamma-ray flash events, but don't worry, there are no known GRB candidates pointed at us. Yet. What matters here is that jets, once again, are central. Whether it's a feeding black hole, a binary system flaring up, or the moment of death for a star, the universe has one signature move. Launch a jet, channel the chaos, beam the energy, leave a trail of light so powerful it echoes across billions of years. And the most extreme version, the GRB, a cosmic exclamation mark. And now, as the light fades, you realize how fragile even the brightest jets are. Which brings us to another kind of edge, the limit of our own tools. Let's talk telescopes, resolution, and what we haven't seen. Yet. You drift now in a calmer region of space, far from the screaming hearts of quasars, the hiss of neutron star collisions, and the searing flash of gamma-ray bursts. The afterglows are dimming, the jets are ghost trails. All around you, silence. But somewhere in that silence, faint light pulses across time, barely strong enough to reach your imaginary visor. You can feel it before you see it. The subtle hum of detection, the shiver of an ancient signal reaching the edge of human knowledge. Welcome to the limits of our telescopes, because as dazzling as black hole jets are, we've only seen a fraction of what's really out there. Much of what we think we know comes from observing the after effects, the lobes, the shocks, the radiation left behind. But the heart of the system, the launch site, the jet base, the event horizon itself, still mostly a blur. Let's be honest, taking a picture of a black hole jet is like trying to photograph a lightning strike from the moon, while the bulb is dimming. You need extraordinary resolution, timing, and a bit of luck, which is exactly why the Event Horizon Telescope, EHT, changed everything. You probably remember that iconic image from 2019, the shadow of a black hole at the centre of galaxy M87, a glowing orange ring surrounding a void, like a cosmic donut that took the world by storm. That shadow. It wasn't the black hole itself. It was the silhouette cast by its event horizon against the glowing material behind it. And in that glow, barely visible, there were signs of jets. But capturing that image took 8 telescopes on 6 continents, synchronized to function like a single Earth-sized instrument. It took years of data processing and more hard drives than a conspiracy theorist's attic, and it was worth it. Because in that fuzzy ring, we saw evidence of motion. In follow-up work published in 2021, scientists examined the polarization of the light, how the electric fields of the waves were aligned, and found that it traced magnetic fields spiraling around the black hole. And that's the structure you'd expect at the base of a jet. Historians still argue whether this counts as direct jet imaging, or just strong inference. But either way, it was the first time we could see magnetic field lines near the event horizon. Not in a diagram, not in a simulation, but in a real object, 55 million light years away. And guess what? We're just getting started. In 2022, the HT team released a similar image of our own black hole, Sagittarius A star, a comparatively modest supermassive black hole at the centre of the Milky Way. Its mass is about 4 million suns, and yet it's hard to study. Why? Because we're seeing it through a thick soup of interstellar dust and gas. It's like trying to photograph a candle from across a crowded smoky bar, through a keyhole with a phone from 2007. Still, we saw it, and we're working on more. Future upgrades to EHT, and upcoming observatories like the Next Generation Very Large Array, NGVLA, and James Webb Space Telescope are going to give us higher resolution, better sensitivity, and maybe our first clear images of jets being born. Because as of now, we've never seen a jet form in real time at its base. We've seen the lobes, we've seen the trails, we've seen blazers pointing right at us. But the moment of jet ignition, the spark that pulls energy from a spinning black hole and shapes it into a column of light, still hidden. Here's your quirky tidbit. In 2010, scientists observed a black hole in a nearby galaxy, NGC 4845, suddenly brighten in X-rays. It turned out the black hole had devoured a super-Jupiter-sized planet. The flare lasted a few weeks, possibly a jet, briefly ignited, then quenched. That's the best we've got so far for watching something start. Even our most sensitive radio telescopes only capture snapshots, not live footage. We observe jet structures at different ages, in different phases, from different angles, and try to assemble the story like some intergalactic jigsaw puzzle made of scattered Polaroids. And what we're learning is that jets are messy. Some bend, some curve, some flare intermittently. We now believe many jets might be intermittent by nature, switching on and off over thousands or millions of years. Others may flicker in short cycles as accretion varies. Without long-term high-resolution monitoring, we're mostly guessing. But here's the good news. New observatories are changing the game. Telescopes like Meerkat and LOFAR are giving us stunning wide-field radio images that show entire jet systems in exquisite detail. Meanwhile, X-ray and gamma-ray observatories are revealing the energetic aftermath, regions where jets have impacted surrounding gas and sparked new activity. And yet, even with all of this, the central engine remains elusive. It's a bit like hearing a symphony from across the street. You know where the music is coming from, you can tell it's powerful, but you still haven't seen the instruments. You've never caught the conductor in the act. We're close though. Some theorists believe that within a decade we'll resolve the innermost jet region, the launch nozzle, if you like, where magnetic fields and relativistic particles first align. That's where the real answers hide. Is it the black hole's spin doing the work? The disk's turbulence? A handshake between both? When we see it, really see it, we might finally solve the question that's lingered since the first radio lobes were discovered. How does darkness make light so sharp, so fast, and so far-reaching? Until then, we keep watching. We build bigger dishes, we link more telescopes, we stare at blurry shadows and noisy data, hoping for a pixel that makes the mystery just a little clearer. Because the black hole may be invisible, but the trail it leaves? Impossible to ignore. And speaking of trails, let's follow one closer to home, because black holes with jets aren't just out there. They're right here, in your galactic backyard. You've travelled across billions of light years, seen quasars blaze and jets carve galactic bones into glowing sculptures, but now it's time to come home. You turn your attention inward, toward the familiar spiral arms of the Milky Way, drifting lazily in a sea of galaxies like a cosmic slow dance partner. The stars here feel warmer, closer, quieter. But don't let that fool you. Because tucked deep inside the heart of this quiet spiral is a black hole, and it's not just any black hole, it's Sagittarius A star. And though it's currently napping, this supermassive object is capable of the same breathtaking violence you've witnessed elsewhere. It's our own local paradox, mostly silent, barely active, and yet sitting at the gravitational centre of everything you call home. Sagittarius A weighs in at about 4 million solar masses, not the heaviest in the universe, not by a long shot, but still more than enough to reshape space and time like taffy. It's about 26,000 light-years from Earth, nestled behind thick clouds of interstellar dust and gas. That makes it invisible to optical telescopes, but not to radio or infrared eyes. You float now above the galactic centre, in an environment where stars orbit so fast it makes the solar system feel like it's standing still. One of those stars, S2, whips round the black hole in a tight elliptical orbit, reaching speeds over 7,600 kilometers per second. Every time it swings near Sagittarius A star, it puts Einstein's theory of general relativity through another stress test. In fact, it was the study of these stars that gave us some of the best evidence that Sagittarius A star is, indeed, a black hole, and not some bizarre dark cluster of neutron stars or invisible exotic matter. Only something with intense compact gravity could make stars do what they're doing. But here's the thing that still catches people off guard. Our galaxy's central black hole is quiet. No bright accretion disk, no superluminal jets, no feeding frenzy. It's there, it's massive, and it's mostly dormant. Historians still argue whether Sagittarius A used to be more active, and the evidence suggests it probably did. High-energy X-ray echoes found in surrounding gas clouds imply that the black hole flared up about 100 to 300 years ago, possibly after swallowing a gas cloud or an unlucky star. The scale of that flare. It might have briefly lit up the galactic core like a mini quasar, but today, it's mostly whispering. And here's your quirky tidbit. Despite being so quiet, Sagittarius A* is occasionally caught burping. In 2012, NASA's New Star X-ray Observatory picked up a series of flares from the region. They weren't jets in the classic sense, but they were energetic bursts, possibly the result of magnetic reconnection in the inner accretion flow. Like a sleeping dragon that twitches when it dreams. Still, the real excitement came in 2022, when the Event Horizon Telescope captured the first image of Sagittarius A*, a blurry ring, less defined than M87's famous donut, but unmistakably the shadow of a black hole in our own galaxy. The image confirmed the mass, the size, the structure, and showed once again that even in its nap, the black hole is shaping the galactic center. But jets? Real, visible, relativistic jets from Sagittarius A*? We haven't seen them. Not yet. Some models suggest it could produce a weak jet, maybe even a stealth jet, so faint and slow that it blends into the background. Others argue it's simply underfed, starved of the dense, chaotic gas clouds that supercharge other galactic cores. Without fuel, the engine just idles. But jets in the Milky Way? Oh yes, we have those. Enter microquasars again. Remember them? Small stellar mass black holes in binary systems, flinging jets like they're bigger cousins. Well, several of them live right here in our neighbourhood. One of the most famous is Cygnus X1, the first black hole candidate ever discovered and a proud member of the Milky Way. It's a stellar mass black hole, about 21 times the mass of the Sun, locked in a binary orbit with a massive blue companion star. As material flows from the star into the black hole's accretion disk, it heats up and emits X-rays. And yes, this system has produced jets, moving at a significant fraction of the speed of light. For a while, Cygnus X1 was thought to be launching a continuous outflow. More recent studies suggest the jets are intermittent, flaring when conditions align just right. Then there's V404 Cygni, another stellar mass black hole in our galaxy. In 2015, it erupted in a spectacular X-ray and radio flare, jets included. These jets were fast, variable, and as chaotic as anything we see in distant galaxies. The entire system lit up in a flash, then faded again, like a tiny impatient quasar trying to make a point. And if you're looking for something even closer to home, well, here's a fun fact. The Milky Way may have relic jets extending tens of thousands of light years above and below the galactic plane. They're faint, ghost-like, but visible in radio and gamma-ray maps as two vast structures known as the Fermi bubbles. Some astronomers think they're the ancient remnants of an outflow from Sagittarius A*, created during a more active phase millions of years ago. If that's true, our galaxy once launched jets that ballooned into massive lobes then quieted down, leaving only the outlines behind. Kind of poetic, right? You float above the galactic plane now, gazing down at your spiral home. The arms curl like sleeping serpents, the stars blink softly, and at the very centre, that sleeping black hole, still powerful, still spinning, still capable of flaring back to life. Maybe someday it will wake up. Maybe it will launch jets again. Maybe you'll see it. Not across space, but across time, in the signals we've yet to detect. Because black holes don't vanish when they go silent. They linger, they wait, and sometimes they surprise us with just how close they really are. But what if some of those surprises aren't natural at all? Let's ask a very dangerous question. Could some jets, just maybe, be artificial? You've followed black hole jets across the universe, seen them light up galaxies and pierce the void with terrifying elegance. You've watched stars fall apart, neutron stars throw tantrums, and entire galaxies change their structure under the influence of a well-aimed beam of plasma. The physics is weird, sure, but it mostly makes sense. And then someone somewhere asked the question you're probably not supposed to ask out loud. What if these jets aren't all natural? Now hold on. Before we start scanning the skies for spacefaring civilizations armed with interstellar particle cannons, let's remember there's no good reason to assume that any of the jets we've seen must be artificial. Black holes are already nature's most ridiculous engines. They don't need help from aliens to be extreme. But there's a tantalizing fringe thought that's haunted astrophysics conferences and sci-fi writers alike. What if an advanced civilization figured out how to use a black hole? Not just orbit it, or mine it, or study it, but engineer it. Let's entertain the idea for a minute. You float now in the emptiness above a spinning black hole, not unlike those you've seen before, but this one feels different. The jet is unusually straight, unusually regular, not just focused but modulated. It's pulsing in clean, precise intervals. A cosmic Morse code, maybe. Here's how the speculation goes. A sufficiently advanced civilization, what we'd call a Type 2 or Type 3 on the Kardashev scale, might be capable of harnessing the energy of a black hole, not just by tapping the accretion disk like a stellar battery, but by manipulating the magnetic fields and feeding streams of matter in carefully timed doses, triggering jets on purpose. They might then use those jets as beacons or thrusters, or, yes, communication devices. Historians still argue whether anyone in the serious scientific community believes this is more than a mental toy. Some do. In fact, physicist Freeman Dyson once mused that advanced civilizations might use extreme astrophysical systems as tools, since those are the only things big enough to do meaningful work at a galactic scale. And in 2020, a paper floated the idea of black hole starships, spacecraft that could orbit a spinning black hole, feed matter into it, and extract energy through the Penrose process or even the Blandford-Znajek mechanism. The energy extracted could then be redirected into a jet, a controlled jet. In this highly speculative model, a jet becomes not just a side effect, but a feature, a product, a signal. Here's your quirky tidbit. The idea that an alien civilization might use modulated quasars to communicate across galaxies has actually appeared in peer-reviewed journals. One proposal involved encoding binary messages by slightly changing the brightness or direction of a black hole jet, over long time scales. It's not exactly a TikTok post, but if you're working on galactic timescales, it might be enough. Still, let's pump the space brakes. We found zero conclusive evidence that any black hole jet is artificial. No patterns, no repeated bursts, no anomalies that can't be explained by natural magnetic fields, relativistic beaming, or chaotic accretion behavior. It's fun to speculate, but the data, it plays by the rules of physics, messy, wild, and beautifully random. And yet, a few odd cases persist. Some blazers, those super bright jets pointed directly at Earth, have shown quasi-periodic oscillations in their brightness, as if they're flickering on a schedule. Is it because of precessing disks, interactions with nearby stars, or is there a possibility, however slim, that something, or someone, is tuning the system? Astronomers are cautious. Pattern hunting is a dangerous game. Find enough data and your brain will conjure all kinds of symmetry out of noise. Still, the possibility of techno-signatures, indications of alien engineering in astrophysical phenomena, has become a real field of study. And it's not just black holes. Some researchers look at fast radio bursts, odd infrared sources, even Dyson sphere candidates, yes, that old chestnut, and ask whether they might be the byproducts of advanced technology. Most end up with natural explanations, but the search continues. You're floating again now, watching a jet ripple with seemingly perfect intervals. You know it's probably just a binary black hole system, one wobbling as it orbits the other, causing the beam to sweep like a lighthouse. But for a moment the timing seems precise, almost deliberate. What if you were watching a message? A signal not made for us but simply visible to us? What if black hole jets are the only language big enough to last across the ages? Let's step even further into the speculative fog. Imagine a civilization so advanced, it no longer builds physical structures. Instead, it shapes magnetic fields at planetary scales. It feeds matter into black holes not for disposal, but for power conversion. It uses jets as propulsion systems, steering vast arcs through intergalactic space by harnessing relativistic recoil. In this vision, jets aren't accidents, they're tools, and a black hole isn't a monster, it's infrastructure. Now back to reality. You check the telescope logs, no binary codes, no braille in the beam, just the usual noise, magnetic knots, flare-ups, cooling shock fronts, everything explainable. Still, the idea lingers, and maybe that's the point. Even without evidence, asking the question pushes us to refine our understanding, to build better instruments, to look closer, to question whether we're truly alone. Because if someone did want to be noticed across millions of light years, a black hole jet would be hard to miss. And as wild as all this sounds, it's arguably no stranger than the natural processes we've seen so far. Matter orbiting at near light speed, magnetic fields launching beams that punch through galaxies, gravity shaping light. The universe already behaves like a special effects reel. Who's to say it doesn't have an audience? But let's ground ourselves again. Before we start building black hole message decoders, maybe we should try something smaller, like making black holes in a lab. You ready for that? Because scientists are trying. So you've chased black hole jets across galaxies, entertained the idea that someone, or something, might be sculpting them on purpose, and now you're wondering, could we ever do that? Could humans, or at least our machines, recreate a black hole and its infamous jet right here on Earth? Well, the short answer is no. The slightly longer, more exciting answer is, we're definitely trying. Let's clarify first. No one is out here assembling actual black holes in their basement. What scientists are doing is trying to simulate the conditions near black holes using particle accelerators, powerful lasers, and incredibly precise magnetic fields. The idea? Recreate just enough of the extreme physics involved, intense energy density, tight magnetic loops, ultra-relativistic particles, to mimic the processes that form jets at a scale small enough to manage, but complex enough to learn from. Welcome to the strange world of lab-made mini black holes. Almost. Let's start with the most famous tool in this particular shed, the Large Hadron Collider, LHC. Tucked beneath the French-Swiss border, this 27-kilometre ring accelerates protons to near the speed of light and smashes them together. In doing so, it recreates conditions similar to those just after the Big Bang, temperatures and densities you won't find anywhere else outside of a dying star or a very bad sci-fi plot twist. Now, back in the early 2000s, there was a brief ahem panic. Some media outlets, and a few very excitable individuals, worried that the LHC might accidentally create a micro-black hole that would consume the Earth. Spoiler, it didn't. But here's the interesting part. Theoretically, under certain models involving extra dimensions, yes, those, it might be possible to produce tiny fleeting black holes at the quantum level. These wouldn't be dangerous, they'd decay almost instantly via Hawking radiation. But if we ever spotted one, it would be an absolute goldmine of physics knowledge. So far, no black holes, but the search continues. Historians still argue whether the early fears around LHC micro-black holes were ever scientifically grounded. Most physicists agree the risk was zero, and some secretly hoped a black hole would appear, just long enough to tell us something new about quantum gravity. But particle physics is just one route. Another, more recent approach involves using high-powered lasers and plasma jets to simulate black hole physics in miniature. In 2021, researchers at Osaka University in Japan used lasers to produce a plasma jet that displayed behavior strikingly similar to astrophysical jets, collimation, shock fronts, and instabilities like the ones we observe in radio lobes. Granted, this jet was about the length of a grain of rice, but in terms of physics, the principles were eerily familiar. Magnetic reconnection? Check. Relativistic particle flows? Check. Jet formation from a tight energetic source? Check, double check. You're floating now, imaginatively, inside one of these experiments. The scale is microscopic, but the energy density is immense. You watch as plasma flows along magnetic field lines, forming a narrow stream. It's not bright enough to power a galaxy, but the dynamics mirror the real thing. We're not creating black holes, but we're modelling them. Here's your quirky tidbit. In 2019, scientists used graphene sheets, a form of carbon just one atom thick, to mimic a black hole's event horizon for electrons. They created a situation where the flow of electrons in the material behaved as if it was trapped behind a horizon. It's not exactly a space-time singularity, but it's one heck of a metaphor made physical. These analog black holes are called dumb holes, or acoustic black holes when using fluids. In those experiments, sound waves play the role of light, and a rapidly flowing medium creates a region from which sound cannot escape. Even here, researchers are studying jet-like emissions, fluid outflows from rotating vortices that behave like jets in simplified models. Again, no gravity wells, but the math lines up. All of this speaks to a growing truth. Sometimes the best way to understand the universe's most complex machines is to build toy versions of them and watch what happens. So why does this matter? Because real black holes are far too distant, too extreme, and, let's be honest, too uncooperative to study up close. But by building scaled-down analogues in labs, we can isolate the key variables: spin, magnetic field strength, accretion flow, plasma density. We can test how jets form, why they precess, what causes them to flicker or fail. These lab models can validate or invalidate simulations, many of which are built on massive assumptions. Remember, we can't see jet launch zones directly, so we simulate them based on what our models predict. If a lab experiment shows something unexpected, it could reshape what we think we know about jet physics. And the implications go beyond black holes. Jet behaviour shows up everywhere in astrophysics. Young stars, neutron stars, even planetary atmospheres display jet-like flows under the right conditions. Understanding the core mechanics of jet formation could have ripple effects across all of astronomy, and maybe even fusion energy and plasma physics here on Earth. But let's swing back to those black holes. Despite all the lab cleverness, we're still missing the main prize: a clear understanding of how gravity, magnetism, and plasma interact at the edge of an event horizon to produce a jet. There's no chamber on Earth that can recreate that. Not yet. But maybe one day we'll build a space-based lab, an artificial satellite that orbits a black hole, armed with instruments to watch the jet form in real time. Maybe we'll send probes near dormant black holes to watch for flare-ups. Maybe we'll harness laser interferometry at such precision that we can hear a jet in the gravitational waves it emits. Because that's the final frontier here, not just to see the jet, but to understand its heartbeat. Until then, we build what we can, scale down the universe into chambers and coils, and watch tiny jets rise in glass boxes and vacuum chambers, knowing they're the children of something much larger, much darker, and far more powerful. And now, standing at the edge of theory and technology, you might be wondering, does all of this break the laws of physics? Or does it rewrite them? Let's step into the realm where black holes and philosophers start sounding suspiciously similar. You're drifting now at the intersection of physics and philosophy, where the rules of reality begin to blur and the edges of knowledge fray like the hem of an old spacesuit. Because black holes, and especially their jets, don't just test the limits of science. They start to ask uncomfortable questions about the nature of information, time, and whether the universe is playing by any rules at all. And no surprise, philosophers have noticed. Let's rewind for a moment. When matter falls into a black hole, it passes through the event horizon, that cosmic boundary beyond which no information can escape. Nothing gets out, not light, not atoms, not your best intentions. It's a one-way trip. We've covered this. But here's the catch. Information is supposed to be conserved in the universe. That's one of the most sacred rules in physics. You can scramble it, stretch it, set it on fire, but you're not supposed to erase it. And black holes, they seem to erase it. Cleanly. Completely. As if the universe just went, shh, no more questions, and clicked delete. This contradiction is called the black hole information paradox, and it has haunted theoretical physicists for decades. Stephen Hawking famously proposed that black holes emit faint thermal radiation, what we now call Hawking radiation, and that over billions of years they would eventually evaporate. Great, except the radiation is random. It doesn't carry information about what fell in, so if the black hole disappears and the radiation tells you nothing about what it swallowed, then where did the information go? Historians still argue whether Hawking's original proposal broke the rules of quantum mechanics or just the patience of his peers. Some believed he was right, that black holes were nature's paper shredder. Others insisted there had to be a loophole, that somehow the information was encoded in the radiation, just impossibly scrambled. More recent theories lean toward preservation. Maybe the event horizon isn't truly a point of no return. Maybe it's fuzzy or chaotic or layered with soft hair that stores quantum information in subtle ways. Maybe Hawking radiation does carry information, just encoded in ways we don't understand yet. But what does this have to do with jets? Everything! Because jets are the last thing we can see before matter crosses the horizon. They are, in many ways, the information we do get. The final flash, the last broadcast. Imagine a star is torn apart by a black hole. Half of its material is swallowed. The other half is flung out in a violent jet, carrying with it data, the chemical fingerprints of the star, the velocity patterns, the magnetic configurations. That jet is not just a beam of plasma. It's a story. Jets may be the only way we witness what the black hole consumes. And here's your quirky tidbit. Some researchers have proposed that black hole jets could play a role in resolving the information paradox by acting as a kind of quantum leakage mechanism. That the outflows, shaped by what fell in, might carry off some form of encoded memory. Not enough to break the paradox, but enough to suggest that the universe isn't just sweeping secrets under the rug. Still, the problem remains. We don't know what happens to information that crosses the event horizon. Some theories say it's stored in a holographic shell, a kind of 2D projection on the surface of the black hole that encodes the 3D information within. Others propose firewalls, hypothetical layers of violent quantum energy at the horizon that destroy in falling information, and potentially anyone bold enough to jump in. It's philosophical dynamite, because it forces us to ask, is the universe fundamentally predictable? Is reality deterministic? Or do black holes punch holes in causality? Can anything truly be lost, or is loss itself an illusion? You sit with these questions now, watching a jet spiral through space, aware that somewhere behind it, matter has vanished. It once had temperature, composition, momentum, purpose. Now it's gone. Unless it isn't. The tension here is that both general relativity and quantum mechanics are correct, but in black holes they clash. Relativity predicts the event horizon and singularity. Quantum theory demands that information be conserved. And somewhere in the middle, jets erupt, seemingly obeying both. You could think of black hole jets as the liminal space between theories, the physical manifestation of space-time warping and magnetic fields dancing, but still governed by quantum rules that we barely understand. They are what happens when equations don't quite get along but still manage to put on a light show. And this has led some thinkers to suggest that black holes, far from being dead ends, are gateways. Not to other universes, sorry sci-fi fans, but to new physics, to a unified theory of quantum gravity, to a better understanding of space-time, matter, and maybe even consciousness. Too far? Maybe. But remember, time itself behaves weirdly around black holes. From far away, things seem to slow down infinitely. For the infalling object, time feels normal. Which raises the old chestnut. Does time even exist in the way we experience it? And if jets form just outside the event horizon, are they anchored in time, or do they straddle it? Here's a thought. Jets may be shaped not just by what a black hole consumes, but when. A kind of chronological signature, a timestamp embedded in radiation, a whisper of events we'll never fully witness. All this has led philosophers and physicists alike to ask whether black holes are computational objects, processing information in some unknowable way. Are they engines of entropy, memory vaults, the universe's own backup hard drives? We don't know, not yet, but we do know this. Black hole jets are not random. They are shaped by mass, spin, magnetic fields and structure. They reflect their origin, and that makes them meaningful. In a universe where so much is chaotic, black hole jets show structure. In a cosmos where silence reigns, jets speak. And where information seems to disappear, jets remind us that some part of it, however faint, always escapes. So you sit with the questions, with the paradox, with the jet still glowing faintly in the void, and realize the darkest parts of the universe don't silence us, they challenge us. And just ahead, one final scene awaits, the moment where darkness becomes light. You're hovering now on the edge of a cosmic conclusion, not the end of a jet or a journey, but the tipping point where everything we've explored loops back into a single, breathtaking truth. Black holes, the universe's darkest entities, are among its brightest sources of light. And it still doesn't quite make sense, does it? A black hole, by definition, allows no light to escape. Yet some of the most luminous phenomena we've ever detected, from quasars to gamma-ray bursts to blazars that pulse with terrifying precision, are the direct result of black holes doing what they do best, pulling things apart. This isn't just poetic irony. It's a paradox carved into the very physics of reality. The jets, the disks, the lighthouses of the deep sky, they don't emerge from the black hole. They're formed just outside its boundary, where space, time and matter are stretched into submission, where magnetic fields twist into ropes and space-time curls around like a spilled drink on a tablecloth of logic. And from that chaos, a beam, a jet, a message. You can picture it now, a galaxy spinning in silence, dust swirled in its spiral arms, stars burning away like clocks with molten hands. At its centre, a black hole, not shining, not glowing, just pulling. But around it, a disk of matter falls inward, glowing hot. Magnetic fields writhe, and at the poles, two impossibly narrow streams erupt, twin pillars of energy so focused they stretch across intergalactic voids, outshining all the stars in the galaxy combined. For millions of years the jet blazes, then suddenly it stops, the silence returns, but the jet's fingerprint remains, etched in gas clouds, radio lobes, and sometimes in the birthplaces of new stars. Historians still argue whether black hole jets played a foundational role in galactic evolution, or if they're just flashy side effects of accretion. But one thing's clear, without them, the universe would look very different. Here's your final quirky tidbit. In 2019, astronomers discovered a double helix-shaped jet coming from a black hole in the galaxy PKS 0637-752. It looks like a DNA strand twisting through space for light years. Why? Possibly due to precession. Maybe the black hole is dancing with a companion, or the disk is wobbling as it feeds. Either way, it's the universe literally braiding light out of darkness. You've seen that these jets are more than just radiation. They're the aftershocks of gravity, shaped by matter and spin flung outward by invisible hands. They're structure in chaos, order in collapse. And here's what's wild. We're only just beginning to understand them. New instruments will bring us closer to the event horizon than ever before. Upcoming observatories, both in space and here on Earth, will watch jets form, bend, flicker, and fade in real time. And one day, we may witness a black hole flare back to life, lighting up jets that have been dormant for eons. Because black holes don't die, they wait, and sometimes they shine, They shine by accident, they shine by force, they shine by turning destruction into motion and silence into signal. They shine because gravity, when given structure, creates order. And when given enough matter, it writes poems in plasma. You float back now, watching the many examples blur together in your mind. The microquasar flaring in a neighbouring system, the quasar beaming from 10 billion years ago, the neutron star slinging particles like it's got something to prove, and through it all the same engine, gravity, magnetism, motion, collapse, and light. So here you are, looking into the darkest part of the cosmos, and what do you see? A jet, a flame, a beam, light, born not in spite of the black hole but because of it. It's a final, beautiful contradiction. The thing that traps all light gives birth to the brightest objects in the universe. And now, dear traveller, dear stargazer, dear soul adrift in science and silence, it's time to let the image fade, to let the jet cool, to feel the glow fall behind your eyelids. Because even the universe needs rest. Even jets flicker and fall quiet, and even curiosity knows when to sleep. So let go. Let the plasma drift into memory. Let the last photon fade, because the journey was real. The questions are eternal, and the dark is never quite as silent as it seems.